Alright, so we arrive at our last lesson for Unit 8. So here are some warm-up questions to help us think about what we may know about this topic before and what we might be learning about this topic and why we might need to learn about this topic. Okay, whatever this topic may be, as to be unveiled in the next slide. So to the best of your abilities, explain how the following devices work. Radio stations and radios, and wireless chargers. Okay, please take a moment to answer these questions, and when you're ready, resume the video to move on to the next slide. So 8.6, we're looking at electromagnetic waves. All right, today's more of a history lesson. There's not really an experiment planned, or at least if you were in class instead of watching this video, we can't really do a lesson with this. Okay, so some announcements. The Unit 8 notes are going to be due on 4/29 for 5th period and 4/30 for 4th and 6th. Late work will be due 5/3, and then Unit 8 test will be on 5/3 for multiple choice, and then 5/4 for free response, even though it should say 5/4, it says 5/3 right there. So what we're up to today, what are electromagnetic waves? How are they discovered? How are they used in modern applications? And how do electromagnetic waves affect our perception of reality? So we'll look at some metaphysical stuff as well. Perhaps not metaphysical, but, oh, what's the word I'm looking for? Huxleyan type stuff, I suppose. The doors of perception. So, electromagnetic waves. All right, let's jump to a little bit of history lesson. So, James Clerk Maxwell, famous Scottish physicist, also the first person to make a color photograph. Okay, in 1865, which, to give you some historical context, is the year the American Civil War ended, Scottish physicist James Clerk Maxwell formulated a series of equations that connected electricity and magnetism. These are the equations that actually describe things that we've seen in the past couple of lessons with Faraday's law and Ampere's law. In fact, Faraday's law and Ampere's law are two of the Maxwell equations. We just haven't expressed them mathematically because mathematically they involve a bit of calculus, okay? So from these equations, he predicted the existence of waves consisting of oscillating electric and magnetic fields, electromagnetic waves. All right. And what's interesting is he actually predicted, based on his calculations, that these waves should propagate at a certain speed, specifically the speed of light. So according to his calculations and his theory, light is an example of an electromagnetic wave. All right, so, however, this is just a theory and prediction. We're not sure if it was correct, okay? So now we need to find the electromagnetic waves. We need some experimental evidence that they're actually correct, okay? So this occurred in 1888 through 89 by a man by the name of Heinrich Hertz. You gotta say it with a German accent. He is the man for whom the Carbontal Agency is named. No, I'm kidding. He's the man for whom the unit for frequency is named, Hertz, okay? HZ for short. So what Heinrich Hertz did was he set out to find, I actually can't recall correctly if he's discovered this serendipitously through serendipity or if he intentionally discovered these, but Heinrich Hertz discovered EM waves in 1888 through 89, and the basic experimental setup he used was he had the circuit that consisted of a spark gap such as this right here, okay? What he had an example of was just called an RL circuit right here, okay? We're not going to worry too much about the R and the L. We're just going to worry about the spark gap. So essentially what happened is when he got his circuit to work, a spark was produced by the spark gap right here. When the voltage was high enough, the electrons from the air in between the gap would be stripped and a current would flow due to a brief spark. And a brief spark would be produced in between the gap. Hence why we call it, well, you guessed it, a spark gap, okay? So the spark ended up producing an electromagnetic wave. In this case, radio waves in the case of Hertz. How do we know these waves are produced? We can't just see waves. It's not like they're screaming, we're waves, okay? So what Hertz actually had set up is he actually set up, this is what we called a transmitter circuit. Hertz had a receiver circuit set up. Notice how this receiver circuit, okay, is not hooked into a battery or a generator or anything like that, okay? So there is no power source for the receiver, okay? But what we notice is when the spark was produced across the spark gap, a corresponding spark was produced in the receiver. And so what that indicated to him is that there needed to be something connecting the two circuits at that time. Something that induced current in the circuit between the two in the receiving circuit from the transmitting circuit, okay? And that led him to deduce, based on what he had read from the work about the work of Maxwell, that an electromagnetic wave was produced by this spark gap in the transmitter circuit, traveled to the receiving circuit, and as a result, induced a current in the receiving circuit and produced a spark gap, or produced a spark in the receiving circuit. To further validate whether this is an electromagnetic wave or not, he also tested and verified further wave-like phenomena for these radio waves. Okay, he saw that they exhibited exam phenomena as light, such as refraction, aka when light bends when it enters a new medium, reflection, and changes in speed due to a medium. Okay, and we come right here. Here's a video that actually shows us this. Okay. In this video, here's our transmitter spark gap, and here's our receiving spark gap. What you're going to see is a spark right here, and as a result, this LED light that's hooked into the receiving spark gap is going to light up. So here is our spark gap. Video is on a lag. All right, let's see if we can pause it here. So we can see there's a spark in the spark gap, and as a result, the LED light right here is lighting up. The only reason there's not a spark right here is because the LED light is connecting the two ends, resulting in a complete circuit. So instead of there being a spark in the receiving circuit, there's going to be a light lighting up. And this acts as validation of an experimental proof of electromagnetic waves, in that the spark right here, spark gap, is sending out electromagnetic waves that's being received by the receiving gap, and that's resulting, or receiving circuit, that's resulting in current being produced in the receiving circuit, as evidenced by the LED light. So what's interesting about this is when Hertz was actually asked about the applications he thought that this would have, his initial quote or response to this was that, "I do not think that radio waves I have discovered will have any practical application," which is quite funny looking in retrospect, because basically all of modern telecommunications is based off this one simple discovery. All right. Well, we look at it as simple now based on the YouTube video, but back then it was profound. It was sparked off a huge new spark. I know, kind of play on words, okay? It kicked off a whole new area of research into electromagnetism and telecommunications. Telecommunications meaning things like Wi-Fi, television, internet, even delving, GPS, even delving into like medicine a little bit, because X-rays are also examples, as we'll see, of electromagnetic waves. And here's the original setup he had as well. Here's the spark gap, and then here's the receiving right here. So electromagnetic waves, let's dig into the anatomy, so to speak, of electromagnetic waves. Electromagnetic waves are oscillating perpendicular electric and magnetic fields traveling throughout space. All right, here's a magnetic field. It's going horizontal in this direction, and then electric field is going to be going vertical. It doesn't always have to be magnetic field horizontal, electric field vertical. It's also equally likely to have electric field horizontal and magnetic field vertical, so, or any mix of the two, so long as the electric and magnetic fields are perpendicular. Okay. These electromagnetic radiation and electromagnetic waves are produced by accelerating electric charges, like the same way that ripples in a pond, the same way that when a boat moves in a pond, it will produce ripples. The same thing happens with accelerating electric charges, as we see right here. Okay. So we can see we have this accelerating electric charge that produces these electromagnetic waves. And when the electromagnetic waves encounter this antenna, this receiving antenna, it causes the electric charges in the receiving antenna to move up and down. Okay? Specifically, the electric field component of the electromagnetic wave is going to cause the electric charge to move in the same direction as the electric field component, okay? The magnetic field component works slightly differently based on Faraday's law. Please note that it has to be an accelerating field. If we have our charge not moving here, okay? If we have our charge not moving here, there's not going to be any electromagnetic field. The charge existing is not sufficient to have, oh, mailbox came up right here. The charge existing is not enough for the, mailbox always does this, it's getting quite annoying. The charge existing is not sufficient to produce electromagnetic waves. The charge moving is not sufficient to produce electromagnetic waves. The charge must be accelerating, speeding up, slowing down, or changing direction. All right. Also, electromagnetic waves will move at the speed of light. C equals 3 times 10 meters per second. You will use that with the wave equation from Unit 7. So the wave equation is going to make a comeback from Unit 7 in order to calculate the frequency and wavelength of light. Okay? So they also electromagnetic waves exhibit the exact same phenomena as those studied in Unit 7, except one thing. They exhibit refraction, reflection, except electromagnetic waves do not require a medium to exist. If you remember from Unit 7, waves require a medium to exist in order for energy to be transferred from one location to another. Electromagnetic waves do not require a medium to exist. And this was actually one of the impetuses for the one of the motivating factors for the development of special relativity. In fact, there's a whole world that you can look into with it. The Michelson-Morley experiment, called the most famous failed experiment in all of physics, all of science. You can look into Henri Poincaré, the French physicist / mathematician, Lorentz transformations, the early works of Albert Einstein. It's a very interesting field in and of itself. The early historical development of special relativity. Okay. So light itself is not all of electromagnetic waves. Light forms a subset, a specific region of the electromagnetic wave spectrum. We call the EM spectrum for short. All right. Specifically, light is the part of the electromagnetic wave spectrum that we can see. It's the range of frequencies and corresponding wavelengths that we can see. There are other frequencies and corresponding wavelengths that we can't see, such as microwaves, radio waves, ultraviolet rays, infrared rays, gamma rays, so on and so forth, okay? And this actually forms, and the colors actually, what's actually interesting, this affects our reality, how we perceive reality, because colors are actually based on how the rod and cone cells in our eyes perceive these different frequencies of electromagnetic waves. So as a think, pair, share here, all right, a brief think, pair, share for y'all. The diagram below shows an electromagnetic wave approaching a conducting wire. Here, all right, our electric field is moving horizontally and our magnetic field is moving vertically. B represents the magnetic field, whereas E represents the electric field. A, we want to know, will current be produced in the wire by the electric field component of the wave? Why or why not? AKA, will electrons be induced to move up and down in our wire by the electric field component of our wave? So focus strictly on the electric field component, okay? And then B, will current be produced in the wire by the magnetic field component? Why or why not, okay? So here's some hints to think about. For the electric field component, okay? Think about, based on the way our electric field is oriented, which way would it push charges in our wire, okay? And then think about, would it be possible for charges in our wire to move that way? And then B, will current be produced in the wire by the magnetic field component? A useful thing to think about is, what is required for a magnetic field to induce a current in a circuit? Okay? Take a moment to think about that, and we'll come back together to discuss. When you're ready, please hit the button on the video to resume. So let's take a look at A here. So for A, our electric field is oriented horizontally, so it's going to push electric charges inside of our wire to the left and right, okay? Or better said, in the horizontal direction in this case, okay? In this case, since there's no space horizontally for the charges to move, no current will flow. If we want current to move, if we want current to flow and we want our charges to move, we'd have to either orient our electric field component of our electromagnetic wave vertically, or we would need to make our wire oriented in the horizontal direction. Okay. Now B, will current be produced in the wire by the magnetic field component? Why or why not? So our magnetic field is oriented in the vertical direction. However, the difference here is that a magnetic field does not interact with the wire the same way the electric field does. The magnetic field is not just going to push up and down on our charges. Rather, the magnetic field interacts with the wire based on Faraday's law. Specifically, the magnetic field needs to be passing through a closed loop of wire in order to induce a charge, in order to induce a current, better said, in the wire, okay? Remember that Faraday's law, a changing magnetic field needs to pass through a loop of wire in order to induce current in the wire. Here we have a changing magnetic field because it's constantly oscillating up and down, but we don't have a loop of wire. We just have a straight vertical line of wire. So as a result, the magnetic field is not going to induce current in the wire. All right. And then lastly, you don't have to memorize the electromagnetic spectrum for a test or anything like that. Heck, even I couldn't tell you all the numbers or anything like that. I'm more concerned if you'd be able to apply the electromagnetic spectrum and be able to understand the electromagnetic spectrum. But for intents and purposes of this course, and just for intents and purposes of general interest, here's the electromagnetic spectrum. The visible spectrum is generally on the scale of protozoans, which are unicellular organisms, okay? And then infrared microwaves and radio waves involve longer wavelengths and hence longer wavelengths and lower frequencies. I said shorter frequencies, lower frequencies, okay? Radio waves are actually about the size of buildings, okay? And then going from visible to ultraviolet, X-ray, and gamma, ultraviolet, X-ray, and gamma have shorter wavelengths and correspondingly higher frequencies, all right? Gamma rays being on the order of atomic nuclei, and gamma rays actually interact highly with electrons in the nuclei of an atom, okay? And that goes into quantum theory and all that stuff, Compton scattering, and all sorts of interesting stuff, okay? And then interestingly enough, the energy carried by these waves is actually proportional to frequency, and this corresponds also to the temperature of bodies emitting light at these certain wavelengths, which goes into black body radiation, thermal radiation, and ultimately, if you want to go into the early history of quantum theory, the ultraviolet catastrophe, which we're not going to go into in this class. But if you're going to go down that line, that's where you'd end up is 1905, Max Planck, and Max Planck was 1899, and Albert Einstein was 1905. But if you want to go down that line, this is how you'd relate temperature to frequency and energy of a electromagnetic wave. All right, and that is 8.6, our last topic for Unit 8.